Okay, good evening, everyone. Today, I'm going to lead a paper discussion because Natasha could not lead it, has poor internet access in the recent weeks. So I'm going to lead it. So I just briefly worked on it and I also copy pasted some information from some other people's material in terms of paleomagnetism. So first, the paper that we read about mainly comes from the Borlina, who is working with Ben Wells, who is the second author from MIT, which is a rivalry against the contents that they're trying to argue against, which is the Turnaro, which we'll talk about later about the work. And Josh Incel is a speaker that is going to give a talk in our webinar this Wednesday, and he also involved in this. So this is the work applying the geomagnetism, geomagnetic analysis on this Hadean Jekyll zircons and trying to reveal that whether this Hadean to early Archean geodynamo is possible or not. So they're basically argue against the evidence suggested by previous workers to say that this evidence doesn't support such a dynamo. So it's interesting. So it's a negative paper to a certain extent. So they're trying to argue against the evidence that this is the case. And it's great that in the scientific community, we allow negative hypothesis to be published because it's important to verify or falsify some hypothesis, I think. So for this work, now let us first go to some fundamentals in this first magnetism and then geomagnetism. So magnetism, that's my understanding that, okay, we do have a dipole north and south, but they're not the geographical north and nor the geographic south. So there is a inclination that we have. So and that could be measured because you know where you are, and then you measure the samples which we are talking about later on, and then you do know this angle that could make difference. And also for paleomagnetism, we know because we know that in Earth, dipole is not a constant; the constant evolves. And this evolvement of Earth's geomagnetic field can be recorded in the rock samples. And so for the rock samples, some of the magnetization are induced by the Earth's magnetic field. But for some other magnetization, which is called remnant magnetization, doesn't depend on the magnetic field. So it depends on the properties of the material. So basically, what do we get for sample is a combination of these two. So we have to exclude one to get the other. And for paleomagnetism, that is extremely important because you may have a sample that lying somewhere, for example, at, for example, Brazil before, and due to plate tectonic processes, end up somewhere in the northern hemisphere. And then that's the northern hemisphere is where you collect sample. So which has a very different magnetic field, which is in very different geomagnetic location than where you get where the samples was originated from tectonically. So you have to remove this Earth's magnetic field influence, especially in the modern Earth, to get the paleo one. So then let's dive deeper into something that going more or geology related, is that Earth's magnetic field is basically is generated by the Earth's outer liquid core. So during this convection of it, and because the twisting of this convecting core and shearing, so it's not a perfectly smooth process that generated this dipole. So it is it is well known for this dipole model, and to use an analogy that people could, let's say, more or less say it's more or less right, 80% or 90%, but it's not perfect because a lot of details still are unknown. And what is more amazing is that Earth magnetic field, that they do have the reversals now and then from the south-north and north-south flip. And during this flip process, the geomagnetic intensity also evolves. So geomagnetic intensity weakens during the reversal time. And when this reverse completes, the geomagnetic intensity comes back. But of course, Earth's geomagnetic intensity is not all the same throughout Earth history. Actually, that's one of the evidence that this paper trying to argue against. And so for maintain a dynamo that needs to go into more process of how the Earth's core could generate dynamo, and that is more equations from physics. But you could think about it. It's related to the core and it's related to the heat. So we do have to consider that different sources of heat is available. For example, the gravitational energy. For example, that is, for example, due to the Earth's inner core crystallization, or the Earth's outer core exclusion of the lighter components, as other different communities talking about in the recent decade or two. Many in the recent decade started from Dave Stevenson from Caltech, I think in 2016 Nature. So that was another one that made the idea popular to pump the geodynamo. And we also have considered their core mantle boundary heat reflux that getting heat away from the core, and as well as the radiogenic. So that's why people care about this radiogenic element concentration in Earth's core, as well as in the mantle too, but for slightly different reason though. So this is important to sustain a dynamo, and we are fortunate to have a dynamo in our Earth, have a magnetic field, and similarly on the Moon, similar physics that could be worked out. Earth, the Moon had a magnetic field, and so does Mars for its early part of the Martian history that it has a magnetic field that could maintain dynamo. Not only for these three that we normally talk about, but for other ones. Actually, I forgot which one. That should be. I think Jupiter. Jupiter has one. Jupiter has a strong magnetic field. For the Sun, in our solar system, have a magnetic field, and also for other small planetesimals, which whether therefore they could form liquid core, and during liquid core convection, they could generate a dynamo. And for some of the meteorites, there's a remnant of meteorites, they could record this geomagnetic information. So, which actually the speaker we're talking about, I think, on Wednesday. So for Earth's geomagnetic field is quite a complex process. I think this is one of the most classic paper, as far as I know, in geomagnetic community, where they could really simulate the geomagnetic field reversal, like more than almost 30 years ago. Actually, that's a very big, important discovery in our entire Earth science community, I would say. So from what they could do is that they could really see this reversal of Earth magnetic field that could occur. So they monitor from the beginning to the end of this reversal process. That's they evaluated about 40,000 years. Although this is very classic work, but there is a simplified version is that they try to set the viscosity very high. So because currently the viscosity of Earth's outer core is 1 Newton meter. I think it's very close to the surface water we have, this water you are drinking. So the viscosity of the Earth's outer core, for example, is very similar to the water you are drinking in terms of viscosity. So it's very viscous because Earth's interior temperature is extremely high. But in this calculation that the people did in the year 1995, they tried to set the viscosity 1 million times higher than that because there's limited computational capacity. So it's much more viscous system that I work with as an analogy. So you may ask that why we are not using the real values now, because people have got a way much better computational capacity. I would say that people tried, but it's very complicated, but it's extremely computation intensive because although the viscosity itself is a 10 to the order 6, but the calculation, I think the computational, the load of work task could increase further by several orders of magnitude. So although people use supercomputing later on to work on some viscosity number that's much closer to your real number, but still we're still far away. from the real viscosity ever. So this simulation is not using exactly the same parameter of the Earth system, but it's pretty good analogy because one good thing that they see the reversal of the Earth magnetic field, which is really great. Okay, so now because Earth has a magnetic field, let's look at the samples so that we record them. So for some of the samples, especially for rocks that we care about, and this paper, for example, basalts in the mid-ocean regions, when erupting at a temperature like say 1300 degrees C and began to cool. So then the Curie temperature for this magnetite, for example, 1 atmosphere pressure is about, for example, 580 degrees as far as I remember. So from 1300 degrees C up to 560 degrees, for example, then let's say you're crossing the Curie temperature, then you begin to magnetize and receive the Earth magnetic field. And so these are the primary ones that are really generated by the Earth, because you have the magma, it cools down, you record what it is. And then and also for some sedimentation, what takes long enough time, they could align according to the magnetic field of the Earth, because it takes some time, but it works. But for this basaltic samples, for example, mid-ocean regions cooling, then it's much more efficient in time. Actually, that's how people figure out the ages of the seafloor spreading theory, actually. Okay, good, I see it. Okay, here it is. Okay, then there is the secondary magnetization, which is not a primary, that's an influence, that's some other process. For example, in this paper, the argument against it is that they do have the Jekyll zircons, and then Jekyll zircons grow larger, for example, and then try to incorporate some other minerals that has a magnetization. Now, but those minerals should not really be the same as the other minerals because they incorporated later and might not record Earth magnetic field. So for those ones, secondary ones are people always trying to argue against. So this is but in the lab that you're basically measuring everything at the same time. Although there are certain ways that people are trying to distinguish the different sources of this magnetism. And so there's a different operators that people have been working on, although it looks not so beautiful, but I think for more science equipment looks like that. And then you do have the magnetization that could be further decreases because the constant increase in temperature to demagnetize of your samples that people are interested in. So here are some more complicated details because when people demagnetize your samples, then people also try in different directions. It's interesting because there's a positive and negative dipole, not positive, yeah, north and south to Earth, but positive and negative as where people look at. You can looking at the oriented at the Earth magnetic field in the laboratory. So there are different kinds of combinations that people could play with, so that you can look at the inclination and declination of the specimens that people are interested in. So of course, people like say here they call it the Washington your specimen. I think another things that people could create a magnetic shield because it could shield away the Earth magnetic field. Actually, if we travel to China University of Geoscience Wuhan with C1 group, that they have the shield room. I think similarly in Beijing, in China's Academy of Sciences, but they have another room that is shielded away from Earth magnetic field. So when you get in, you don't get any Earth magnetic field. But anyway, so that's creating environment like that is useful. And then here's actually I copy pasted for somewhere else for us to understand is that they're trying to increase the voltage, and so that it generate a heat, I think, as far as I know. So then they try to demagnetize your sample, and then you can measure the magnetic strength evolution when you place these different kinds of constraints or to control the magnetic field of the samples that you can measure. So this is some unit that we could think about is I think this is a million Tesla, so 200 larger than the magnetic field of Earth. So we are so we're about 5 micron Tesla, I think, the field. If I'm correct me if I'm wrong. So 1 Tesla actually is quite strong. So this is several orders of magnitude lower than the 1 Tesla, significantly much less than that. So when you place a magnets in your hand as a toy, that basically you have to create a much larger magnetic field than the Earth magnetic field, I think. So back to this paper. So the motivation is that they want to fight with the other group. Actually, I have personally haven't been sitting in the same room with the authors of this paper and this paper they're arguing against. It was almost a fight, and verbally people are yelling at each other. And I was thinking maybe I'm going to watch a boxing game now. People are going to fight, but it didn't occur. I get quite close to that. So it's quite intense argument between these two communities. And for these two communities, one community say, okay, we have these Jekyll zircons, they're old, so measure them, and so it shows that they do have magnets, some paleo intensities that is there. So the Earth used to have a geodynamo, very, very old, as old as 4.2 billion years. So even Haiding will have geodynamo. You see this Jekyll zircons, they recorded them. So that's the argument from Russia's group, leading by Tarduno. And then there are some other group of people are trying to say, no, your samples are wrong. So they want to use different way to show them they're wrong. I think this is one they're talking about. So they first say, okay, the samples because the zircons themselves are not magnetized. Is the inclusion within these zircons so that it could magnetize. Some people say, okay, your samples are not the primary samples. So because when the Jekyll zircons they crystallize from the felsic magmas, then they form the zircons. But these zircons later on they incorporate some other minerals when they grow. So they say these are your magnetism you measure in your samples in your lab. The magnetism are not the magnetism of the really primary ones, but you inquire some samples that come much later. Who knows? Maybe that Archean may be Paleozoic. We don't know. We might maybe way much later. Maybe it was, let's say, in the past 1 million years. You incorporate something that's new. So then, and then they say, okay, they were not shown to contain. But the second point, I think they want to say that because in the later part of the paper they talk about it is that you could encounter some other metamorphic process. For example, your Jekyll zircons is there and formed there, and with maybe together with something else. And then there was an intrusion somewhere very close to this group of sedimentary samples. So basically, you heat it up. So they heat up your samples once you are above, for example, Curie temperature, and then you record the geomagnetic field at the time when this intrusion occurs, which could be much later, maybe Phanerozoic, who knows, maybe 5 million years, something much later. Actually, I think they find some evidence like that, that people argue against. So that's why people do some lithium concentration profile to look at the diffusion rate of lithium in the zircons, which is trace element in zircons lithium. And currently, as assistant professor at the Beijing University, so Tang has been working a lot on that, on lithium diffusion. Actually, in this paper, they also cite that work, I think, to argue against, because looking at the diffusion profile of this lithium, basically you could calculate the possible temperature that they experienced, which could be much later, because if this primary lithium should not have diffusion rate curve, they should be flat because of the primary. And if something like heat up, then the lithium are going to have a bending curve in terms of the concentration because they're going to diffuse away. So the second point and the third point, they say, okay, for the previous people's work, Tarduno, for example, they got the samples, they measure some paleo intensity, but you intentionally let's say you measure the ones that has some paleo intensity. But for a lot of zircons that were there in the Jekyll zircons, you did not select them because they didn't have much paleo intensity. So you just exclude them away for a lot of Jekyll zircons. So maybe those are ones that also could those were the ones that should also be representative of the paleomagnetism, but you didn't count them because they just have just too low intensity. So maybe there's within those zircons are still within the group of samples you have because they collect the detrital zircons that contain a lot of grains. And so you just say, okay, those ones doesn't matter. So I think that they're all trying to argue against the evidence that Tarduno, sorry, it has been listed before, and here are what they are trying to do is they say, okay, we are doing to have some sampling criteria to differentiate the samples, to classify them, to say, okay, whether they pass this necessary test that could convince us at least for this group of speakers, not speakers, researchers. Then they say, okay, they let uranium discordance should be low, less than 10%, because it's too large, that means that you are impacted by some later thermal activity that basically could reheat your samples and remagnetize your samples in some much later time. Who knows how early, how recent they are. So also there should be lack of visible cracks, so to avoid the secondary minerals there, and also so when they also measure the lithium concentration, because they say, okay, you should have very, very narrow diffusion fields, because if you have a diffusion thickness or diffusion profile. So if they're too large, then that means that could basically calculate the temperature, because that based on Tongming's results of the diffusion temperature time versus diffusion providing a laboratory. Okay, so by doing this three constraints, they're trying to say, okay, we begin with 3754 zircons to begin with, and then let's say doing that, then they have only like 10%, less than 10% of them being left with older samples, and then you only for every 5 grains, you have 1 grain that could be used for paleomagnetic studies, and so it is few and few. Basically, they say, okay, none of your samples that really qualify. So for those samples, for example, you can see here, most of them are secondary. That's what they are trying to argue against. And a lot of samples has, let's say, lithium lithium band. I think with less than 20, 20 micron lithium band. Actually, well, maybe we should look at Tongming's data again to say whether 20 microns is reasonable. Maybe should set it larger. 20 micron to me, that looks very, very small. Okay, I don't know the details for that, but look at that, people should figure it out. And then you have the alteration. Of course, you don't want the alteration to occur. Basically, they set a lot of bars to say, okay, none, which is to argue against what it is. Okay, so here are some more data. And then I think these are the YZ axis plot, because in my interpretation here is that you have XZ, because you have samples at different directions that you look at today. You measure them in different directions too. So as we showed much earlier in the slides, that basically there are 24 different possibilities that you are going to measure samples. I think that's how people are trying to plot their intensities they get when you look at the different directions when you apply a magnetic field control in laboratory. And here is just some further examples where they zoom in to look at the lithium concentrations. And so here are the, let's say, thermal remnant magnetic field that they gained actually from this analysis. Actually, I don't really understand vectors subtracted. I don't know. Okay, so they need to subtract a certain amounts. I think so. So maybe we can come back to this later, Sean. So okay, so they're basically showing these two case studies, I think, for the samples that passed the selection, which looks like more primary ones. but let's see. Probably we need to go back for that. I think there's a two. Okay, but this one is that okay, you can't find a voice that doesn't really counts because this voice could be the secondary places where those incorporated in much later process. So basically that should not count as these really old ones because don't have direct dating for them. And I think at the end of it, they also say, okay, not only will measure their micro mechanism, but we also use this quantum diamond microscopy to look at the specific points where they could generate a mechanism. I think that's how they're trying to say to just verify what they observe. I think that's my understanding for it. And then in the end, that they're trying to argue against. So to say why people have different conclusions. So why Tarduno say, okay, they have this paleomagnetism according to this maybe 3,000 samples, the grains, and for them they say none of them could represent the Hagian ones. So so during the preparation, they think that okay, they say that they used a lot of very concentrated, very strong acid to wash away the secondary magnetic deposits. So basically, they say, okay, Tarduno, so you get the samples that a lot of the secondary magnetic deposits basically have nothing to do with the primary samples that should represent the primary mechanism, paleo intensity from the drilled animal, and then they also use some high sensitivity magnetic microscopy. So they measure it and they say, okay, weaker is much weaker RMs. So basically, it's okay. All of these are not primary in origin, so it's really against it. So they say, okay, this sample doesn't represent what is possible. So people need to find some more convincing evidence to say about it. Okay, I think that's so much what I can lead so far. Although the speaker, I think on Wednesday, he's going to talk something that's slightly different. So he himself, as a physicist, that he's interested in mechanism, but also sort of as a physicist, material scientist, as well as earth scientist. So somewhere in between of the three in terms of mechanism. So hearing his 2018 Peanuts paper, he was talking about this different particles, that magnetic particles from the meteorite that were different grain sizes, and also he GP scan to look at different crystal orientation that is related to the mechanism. I think on Wednesday he's going to talk more about that rather than the one actually we are reading today. Although he's a co-author, but I don't know how much he will talk about. I think that's the primary ones is going to talk about on Wednesday. Basically, will be on this slide, not the previous ones so that I led. But I think the previous part is more interesting for geologists. Okay, I think that's about it. So do you have any questions or discussions, concerns, or you can make further clarifications that I didn't clarify? before that, well, if you studied a zircons after the zircon formation, then you just don't know what did they represent, because yeah, you just know, because if zircon now about, let's say, 3.5 billion years ago, and then maybe 1 million years, let's say 2 billion years later, incorporate something that's had nothing to do with the previous ones, but that's going to mess up with your measurement, or your measurement could only represent what happened at 1.5 billion years rather than 3.5 billion years. Before, there's no before. I think all the minerals that people think that are being trapped at zircons, if they're primary, then they should form at the same time of a zircon formation. Not much earlier. Maybe 1 day earlier, or within geological time, it should be exactly the same. Yeah, even 1 million years is nothing for Hadean samples, because they're all old enough that even you get a very low uncertainty for the geochronology. For example, you have 1% uncertainty. Then how much? It's 4 billion years. Then basically you have 40 million years uncertainty in terms of age. You have 1% analytic uncertainty in terms of your Hadean samples. So yeah, for 40 million years, I think this is large enough for any of the samples that form before this zircons form. So that was much larger. I don't think that people could really resolve that. So people consider they're the same time, form at the same time.
So could you hear me?
Yes, Trina, please go ahead.
Yes, the most important, I think the most important area of this paper, I think we just use standards to see whether the zircon just meet the standards of the paper proposed. So if they just observed more than 3,700 zircon in the microscope, I think it's a really huge task to do that. I think I don't know if they observed all of those zircon grains in the microscope. If it is, it's really huge work to see all of those zircons, I think.
I think so. I think they just went through every one, because it's interesting, because although it looks like there are a lot of zircons, but this is just all of this work. I think it's Mark Harrison. Yes, Mark Harrison. So Mark Harrison, his group almost dominated most of Jack Hill zircons in the world at UCLA, I think. So by collaborating with him, that they're dealing with it. But I think they have some more smarter ways to accelerate the look at the details of these zircons, because the whole group that just working on this Jack Hill zircons, that you get those of them that analyze them in every way they could. So yeah, so yes, I do think so. I do think so that they're really looking forward. So for graduate students, yeah, maybe every day they look at 10.
That's why we got so many authors in the paper. I think a lot of maybe.
No, I don't think so. No, it's not. A lot of people, I don't think they really analyze. Let's say some of them involving analyzing samples. For example, Roger Fu is from Harvard University. I think for this quantum atomic diamond, quantum diamond atomic, I think probe is using Harvard because of him. So different people, I think, have slightly different role. I don't think that, I don't think everyone that does the work. I think still is the first author does most of the work, I think. So it is a lot of work. It's true. It's true. The first author does a lot of work in selecting zircons, I think. So another question is a inclusion part. When the zircon encapsulated in inclusion, the inclusion is the liquid phase, right? Not necessarily, depends on temperature. So when zircon forms, actually, I don't know what's the exact temperature that zircon forms. I should know. I think 800, 700 degrees C. So the inclusion depends on what type of the mineral it is. Will crystallize immediately or gradually? Well, that depends on the cooling rate of a rock. I mean, also depends on whether it's exposed out, where it does it exposed to, right? So how long takes crystal induce at the area? Oh, I don't think that this cooling rate will reset time much, because I say even give you 1 million year, that's more than enough for you to crystallize, to cool, even if you cool very slowly. As we talked about before, 1% of age analytic era is 40 million years for this high samples. So if they cool, I think 1 million years is fast enough for this, let's say, near surface samples to really cool. Maybe get multiple millions of years, but that's nothing compared to the high samples. So I don't think that we can really resolve that at all. I mean, it's possible, probably for the very young samples, we could resolve that, but for old samples, I don't think. At least I don't think. Yeah, maybe we should. Yeah, it's a good question. Okay, if that is, I think that's so much about it. Okay, so who's going to show our group video? Maybe we'll look at some progress our group video. Okay, Ben could share about group video, I think.
No, I don't have any our group video.
So maybe Chantal is going to show our group video. I don't know whether you have already managed it or not.
Please wait, I just find it.
Have you found it?
Yes, but I do not upload to my computer. I just it's just in my phone.
Okay, that's okay. That's okay. We could skip. Maybe we could. Yeah. Oh, let's do it at Bilibili. Okay, that's fine. Okay, have a good week, and yeah, see you at the time of the week. Bye bye.